Okay, so our topic for this part of the session then is going to be looking at ratio. So, oh, click the wrong button. Always a good start. Okay, so in regards to this kind of topic, then what we're going to be looking at is an introduction to ratio, what it is. Essentially, it's unfair division. So we're going to have a little bit of a look at this. And we're going to look at our first idea, which is about equivalent and simplified ratios. Very, very, very similar to fractions. In regards to simplify, we are doing the same thing. We are just taking a ratio and we're making it into a nicer, simpler one. Same with equivalence. We're then going to use this kind of idea and this concept to look at these kind of more real-life problems and some of the problems that we're going to see in the exam. So in regards to scales and maps, real-life problems and blueprints. The blueprints is a little bit of a sidestep, but I want to cover that topic because it does tend to use ratios in regards to scale, but it's also something that I just want all learners to be aware of what these questions look like and how best to answer them in the exam. So once we've looked at these are all basically looking at the simplest type of ratios. We're then going to look at our ratio division problems. These are probably the most common type of question that pop up. It's when we've got like an object and we're sharing it between two different kind of parties at a different rate. It is all linked in with our idea of proportion from the beginning. So this will link in and hopefully everyone will get the hang of this. I have got two explanations for it, which I'll go through. It's up to you to choose kind of which one you use. They're essentially both the same. It's just a different way of viewing it, but the sums are all the exact same. It's just a different explanation. So once we've looked at that, we are then going to look at proportion and inverse proportion. And then we have some kind of exam style questions at the end if we want to have a look through them. Main thing to point out is that this kind of concept of inverse proportion, this is something that is only for level 2 learners, and it is very, very uncommon. So it's good to be aware of it. We're not going to spend a long time dwelling on it. It's just going to introduce the idea so you know what it is, essentially. It's a very straightforward idea. All of the topics above are all relevant for level 1 and for level 2. And all of the skills are kind of equally as likely to pop up in regards to questions as well. So with that being said, then let's jump into it. So what is a ratio? So a ratio itself is used to share things out. It relates to parts of a whole, very much like fractions, and how much of the whole different people get. It is very similar to fractions in a lot of ways. So let's have a look, first of all, at what it looks like when we write it down. So what we have, first of all, is if we look here and we've got, what is the ratio of red counters to yellow counters? We're going to write this as 5-3. The important thing being that whatever is asked to come first, so in this case, it's red counters come first, that is the number that goes first. We then have these 2 dots here and then 3. So what this means is that for every 5 counters, there are 3 yellow. That's all that we're saying. Again, if it was worded the other way round, so if it was what is the ratio of yellow counters to red counters, then you would put this as 3-5. And again, you can see some of the links there with fractions. You could say, well, there are 8 counters in total, so 5 out of 8 are red, 3 out of 8 are yellow, for instance. So if we have another look at a ratio here, then what we've got is, what is the ratio here of green to blue? I'm just going to count them. So in regards to the green counters, there are 4 of them. In regards to the blue counters, there are 5 of them. Now, this one here, I've done some amazing wizardry with the PowerPoint. So you're going to notice one of those yellow dots is going to move. It's going to be incredible. Watch it go. It's going to be the highlight of your day. Ready? Oh, there it goes. Amazing. So what we are looking at here then is what is the ratio of red counters to yellow counters? And there was a reason that that counter moved over. So we could write this if we took all of these counters into consideration and write this as a ratio of 6-2, which is completely correct. But what you might be able to see is that now that counter's moved, you can almost split that in half. So we can simplify this and we can say there's actually for every 3 red counters, there is 1 yellow counter. this is simplifying a ratio. It's all we're doing. We're looking at both numbers. They are in proportion. So it is a case of, well, we can half both of them. We can times them both by 3. We could times them both by 100, divide them by 1,000. As long as we do the same to both, it's absolutely fine. It will keep its equivalence. If you imagine, if I was working a job and, we earn £4 for that job, and this person gets £3, this person gets £1. If we double the amount that we got, so say now we got £8 in total, then this person would get 6, this person would get 2. Exact same concept of kind of like those basic ratios that we've already kind of encountered. What I would say is that simplifying ratios is very, very useful. It's a very, very good skill, and it's all about getting the ratio down so that we know what one part is worth. If you remember with our percentages, when we divide by 100, we find what 1% is. Once we know 1, we can build anything. It's the same with ratios. If we work out what 1 is, I can then work out anything, and you'll see more of this when we look at some of the real life problems. So as an idea, we could have a question like this. So Ben the painter needs 6 litres of dark purple. He will use 4 litres of red and 2 litres of blue paint to achieve this. What is the ratio of red tins to blue tins in its simplest form? I'm just going to write it out. So I've got red and blue, I've got 4 and 2. Can I simplify this? Yes, they're both even. I can divide them both by 2, and I've got my simplified ratio. For every 2 litres of red, there is 1 litre of blue. Absolutely perfect. So again, just another example here. So Sarah has a number of white and black counters in a bag. Write the ratio for the number of black counters to the number of white counters in its simplest form. So it is black to white. So it is going to be 3 to 9. Both of these are in the 3 times table, so I can simplify that way. And I can get down to what one part is worth. So in regards to real life, then, we actually see ratios all the time in ideas like this. So let's say, the cost of apples is £1.60 per kilogram. What that means is the more apples you buy, the more it costs. And they are in what is called direct proportion. And that is what will equate to any problems that we find in functional skills. Direct proportion is if I increase one thing by, let's say, 10 times, then the price will increase by 10 times as well. If you were to put it on a graph, it would look like this. It would just be a nice linear line. So again, in context, if it's 1 kilogram of apples is £1.60, therefore 2 kilograms would be £3.20, or half a kilogram would be 80p. 10 kilograms, I've made it 10 times more, would be £16. Very nice and straightforward. And these are some of the types of questions that we might see. I'm going to talk through these ones here quickly, and then I've got a few more examples for us to have a go at next. So for our first example then, if we've got 3 chocolate bars cost 45p, how much will 6 cost? Again, it's very straightforward maths. We don't even have to know what 1 chocolate bar costs because we're aware that the link between these, well, if 3 bars is 45p, 6 bars is just double as much. I've multiplied it by 2. I've got 2 times as much. It will therefore cost 2 times as much. When we've got a ratio like this, if we know what one part is, it makes everything considerably easier for us because we can just see, well, what is the link between them? So here it's £1 is worth €1.56. How many euros would I get for £20? Well, for every £1 I have €1.56. So if I have 20 times as many pounds, I have 20 times as many euros. €31.20 there. So these ones here are these kind of one-step problems. What we tend to find, though, is problems like this third one, where it links in a bit more with what you will imagine with our percentages. With our percentages, if we want to find 30%, there's not just a value that we can divide by straight away. What we do is we find 1% or 10%, whatever we prefer, and then we find that percent. So it's finding the base unit first and then moving upwards or downwards, depending. So in this case, if I've got 2 litres of apple drink contains 800 millilitres of juice, how much juice is there in 3 litres? Again, if I write down what I know that 2 litres are 800 millilitres. Now, to make this easier for me, if I want to get to 3, I'm not entirely sure how to do that straight away. So let's just find 1. If I divide this by 2, then I'm going to end up with 1 litre of drink is equal to 400 millilitres of juice. Okay, that's fantastic. I know what 1 is now. So if I want to get all the way up to what 3 litres is going to be, I'm just going to multiply that by 3. So this first step, I've halved it to find out what 1 is. I've then tripled that to get up to the value that I need. So this is really the main premise that we need here, this idea of find out what one part is worth, use that to then get to the value that you need after. So have a look at this problem, write down what you know, first of all, so how much is 6 litres, and then if you can try and use that to find out how much 4 litres costs. So you're going to have to find out what 1 is first, probably. There are different ways, though. So have a go, and let me know what answer you can get here. Catherine, yeah, absolutely spot on there. Brilliant. So just give it another minute or so for people to have a go at this one, and then I'll go through and explain. Casey, yes, absolutely brilliant. Okay, so for this idea here, and I do think it is really, really worth just looking at this as like a real life problem as well. You know, if I know how much 6 litres is going to be, I need to know how much is it per litre. So to find that out, what I'm going to do is, well, if I know 6 litres is equal to £9, if I divide that by 6, I get to my base value, and I know that that is going to be £1.50. It's the exact same as what we do with our percentages. We divide by 100 to find 1, then we times by what we need. The only difference here is that we're not always working out of 100%. It could be dividing by 80, 84, 12, 4.6. It could be anything. But if we divide by that number, we find 1, and that's the most important thing. What we've now got is, okay, well, I know what 1 litre is. I want to get 4 litres. So I'm going to times it by 4, and you should end up with an answer there of £6. So here is just one more of these then for you to have a go at. So if I know that 8 oranges are £2.40, how much would it cost for me to buy 5 oranges? So again, write down what you know first of all, follow the same steps as above, and you'll be absolutely fine. Okay, brilliant stuff. Yeah, so Nicola, absolutely spot on, and Catherine as well, absolutely brilliant. So this is great. If you're happy with this concept for level 1, this is a very, very common type of question. For level 2, this is essentially the building blocks of what we're going to build onto. So you're doing absolutely great. Katie, that's spot on as well there. So I'm just going to go through and explain this one as well, and then we can get moving on a little bit and see how this links in different kind of contexts. Andrea, yeah, brilliant. So with this then, I've got 8 oranges are £2.40. That means if I divide it by 8, that will tell me what 1 orange is worth. So 1 orange is 30p. If I want to know how much 5 will be, then I'm just going to multiply by 5. So it's that idea of dividing at the beginning to find out what 1 is worth, then multiplying by what you need. It seems strange to do these 2 steps and almost like going backwards before going forwards, but it's just because I don't know how to get from 8 to 5 straight away. There would be a division that you could do. Yeah, if you've done 8 divided by 5 and then worked out the difference, it just seems a lot more complicated. So sticking with this method is definitely the way forward. Now, this is often seen on maps and scales. So this is just one place where they will use this, and it is the exact same skill that they use. So we might see a question like this, where it says, the scale on the map is 1 centimeter to 40 kilometers. What I will point out at this point is say, on the scale or on the map, if it doesn't state the units, then they are the same. So there was a question recently where it said, the scale is, I think it was like 1 centimeter is 100. So what that means is that 1 centimeter on the drawing is equal to 100 centimeters in real life. So we use these scales, obviously, because I can't actually draw a line from here all the way to wherever else in England I want to, because I'd never be able to see it. So we use scale to obviously represent it. So in this case here, then, if 1 centimeter is 40 kilometers, then how far is 5 centimeters going to represent? Again, for me, I think the best way of looking at any of these questions is write down what you know and then use that. So I know this. I'm trying to get to 5 centimeters, and I don't know how much that's going to be. All I have to do is look at what has increased there. Well, I've gone from 1 to 5. It's 5 times bigger, therefore it will be 5 times bigger on the other side as well. So this will have to be 200 kilometers. So hopefully that's quite nice and straightforward. It's the exact same concept as what we were looking at with our questions a minute ago. It's just this is one that pops up quite frequently in regards to kind of they might ask you this on a map. It might be a question where you actually have to measure a distance. So maybe you'll measure the distance, it's 4.5 centimeters, and they'll say, okay, every centimeter is this in real life. How far is it in real life? Something to this effect. As another example here then, so just worded a bit better. So on this map, the distance from Exeter to London in a straight line is 6 centimeters. So what is its actual distance? Same type of question. Well, if it's 6 centimeters there, and I know every centimeter is 40, it's going to be 6 times 40, which is 240. The last type of question is they might ask you to do this essentially backwards. And this is where a bit of our backwards thought can come in really, really useful. So again, if we write down what we know that 1 centimeter is equal to 40 kilometers. In this case, they're saying the actual distance from Birmingham to Manchester is 120 kilometers. What is that on the map? So what you might be tempted to do is go, okay, well, what have I increased by? So from 40, I can go 40, 80, 120. Okay, it's 3 times bigger. Absolutely brilliant. I would recommend trying to look at this backwards and look for what the multiplier is instead. I know that 40 times something is equal to 120. Therefore, 120, if we remember our backwards calculations, 120 divided by 40 will tell me what that something is. So this is the method that I'd say to start using. In this case, it's very nice and straightforward, and we can immediately see what the answer is going to be. Sometimes, though, it might be, if 1 centimeter is 40 kilometers, the distance to, I don't know, let's say Leeds is 281.6 kilometers. When we have a number like that, we're going to come unstuck with this idea of just seeing how many 40s fit into it. similar to when we do any long division problem. If we're trying to see how many of a number fit in, if we have a number that doesn't fit perfectly, then our system will break down. So that's why doing a division is always the better idea here. If I do 120 divided by 40, it tells me that it is 3 times bigger. So therefore, the scale has increased by 3, so my measurement must also increase by 3. Sounds like a very long-winded way around it, but essentially, you know, it's up to you how you look at it. I just think if you're given this information here, if you do 120 divided by this, it will tell you how much bigger it is. So just make sure everyone's quite clear on that. Okay, so we're going to take a little bit of a side step then. There will be some scales involved in this, but I want us to have a look at these blueprint style questions. So we're going to look at a couple of examples of these, one from level 1, one from level 2, although they are incredibly similar. Level 2, you might just get some slightly stranger measurements, etc. There are some simple steps to follow when we're looking at a blueprint style question. What you want to do is, first of all, list the parameters of where an item cannot go. If you mark these out, it narrows down your options. It makes everything easier. Make sure you read the key or the scale and make sure that you're following it. And then finally, make sure do a rough plot in pencil, double check it, make sure you're happy with it, then do it in pen to make sure it's there permanently. So here is an example of this type of question. So Mr. Smith wants to build a platform for the hot tub in the garden. The platform needs to be a rectangular space that is 5 meters by 3 meters, must be at least 2 meters from the back of the house, and must be at least 1 meter from all of the edging. Mr. Smith draws a plan of the garden on a grid. Draw the space for the plan on the grid. And what you'll notice here is it's 3 marks. So you will get 1 mark for each of these. If you draw a rectangle that is that correct size using the scale, you'll get 1 mark. If you draw, and if you meet all of the criteria, obviously you get all the marks. If you just draw an object that is not quite the right size and it's within, 2 meters of the back of the house, but it's 1 meter from all of the other edging, you'll get 1 mark still. So it is just literally process of elimination, tick them off as you go. So this is the diagram that we get given them. And again, you can see down there is a key for this. So what the key says is that 1 square on the grid is a 50 by 50 centimeter square. And the black border around the edge is the edging. So if we start looking into this, then let's make a list of where this object cannot go. So first of all, it's got to be 2 meters from the back of the house. And this is where our scale is going to come in. They are normally as nice and straightforward as these. So I know 50 centimeters is 1 square. Therefore, 2 squares would be a meter or 100 centimeters. 3 is 150. So it needs to be 4 squares away. Using this scale, I can then draw this line in here, or just shade that part out and say, it cannot go any closer than that line. It has to be on the left of that line. I'm then going to do the exact same for the 1 meter from all the edging. 1 meter in this case is 2 squares. So I'm just going to draw around everywhere that is 2 squares away. What that then tells me is that the rectangular kind of object that I have to plot in here will have to go in this space. It can't go anywhere else. It makes it so much easier for me to plot without putting it somewhere and then going, does that meet that and that? Yeah. Okay, brilliant. I might just put it somewhere random and then go, oh, it doesn't work. I'll move it there. Oh, it still doesn't work. I'll move it there. This just saves a lot of time. The last part then is drawing our rectangle in there. So again, it is 5 meters, which means it will be 10 squares because each square is half a meter. And it's by 3 meters, which means it will be 6 squares wide. So this is the shape we're looking at. Hopefully what you can see here is that that is not the only option where this could go. There are variable answers here. It could be 1 square to the left or 1 square to the right. It could be 1 square higher. It could be up 1 and to the left or up 1 and to the right. You could, if you wanted, flip the shape on its side and it would actually fit long ways across there. And I'm sure it could go in multiple places down there as well. So there will be different options for this. We've got another example here then. So we've got Eric wants to put some hair washing stations in a different room. a washing station needs one sink and one chair. The chair needs a rectangular space 60 centimeters by 110 centimeters. One of its shorter sides to go along a sink, or along a side of the sink, and to have at least 50 centimeters of free space around its other sides. Again, it's the exact same type of question. It's just using slightly different rules and slightly different measurements. This is the diagram that they give you. Again, you can see it looks a little bit different. And you can see here that the scale is a bit different. And this is one of the most important things. So it does it is important for level 1 and for level 2. Essentially, what they can ask you to use up to 1 or up to half a square of a degree of accuracy. So here, if I know that each square is 20 centimeters, I know that each half a square is going to be 10 centimeters. They can ask me to use that level of kind of like that level of accuracy. That does also apply when we later look at kind of reading and drawing data. When we're actually drawing graphs and things like this, that same thing can apply as well. So you might be asked to draw in between kind of 2 points. Okay, so let's have a bit of a look then. So first of all, it's got to have at least 50 centimeters of space around all of the sides. So what I know is, well, 1 square is 20, 2 squares are 40. It's going to be 2.5 squares. So I can go around here and I can just make sure it's 2.5 squares away from everything. Again, here it could actually, come out a bit further in this part, but it's not really going to help me. Again, I'm just making an estimate as well. So I know it's going to go in this area. It's got to have one of its shorter sides go along a side of the sink. The shorter side is 60 centimeters, so that will be 3 squares. So I've chosen to place it here across these 3 squares. Again, it could be moved half a square to the left. It could be moved half a square to the right. But with this, you might notice that your choices or your choices are more limited here. It can only really go in this position, one to the left or one to the right. That's the only place it will work. But we found that via process of elimination again. And again, it's 110 long. So that is 20, 40, 60, 80, 100, and then the half there. It doesn't have to be exactly half, so long as they can see that it's clearly not ended on the line or on the next line. It's somewhere in between. You'll get the mark. Okay, so are there any questions regarding that kind of like the scale or anything like that? Is everyone quite all right at the moment? It's quite nice and straightforward, really, those questions, but I do always like to make sure that people are aware of them. You can find questions like that as well. It's one of the few questions where circles can be involved as well. Actually, I'll highlight that now. So you might actually be given, there was a question recently about, there was like a tree at this point and it had roots that could grow out, and the roots could go a maximum of 2 meters away from the tree. So what that meant is obviously you wanted to measure a line that's 2 meters, and then using a compass, you can then draw around so you know everywhere that is within 2 meters of that. But is everyone quite all right with that? Cool. I'm going to take the overwhelming silence of yes, we are fine. So that's all good. Okay, so we're going to have a look at proportionate division then. There is a quick and easy way of solving these problems, and bear in mind it is pretty much the exact same as what we were looking at before. It's just there are 2 things that are in proportion. If we increase one, we increase this. If we decrease it, then we decrease it by the same. It's just that we're sharing things out not to one person, but to more than one. It'll make sense as we go through. Best thing you can do, write down what you know and what you don't know. Always really, really helpful. Then fill in any missing values that you have or any totals that you can find. Catherine, yeah, that's absolutely fine. If you do need to drop out, that's not a problem. Just remember the assessments for completion for tomorrow or for next week, sorry, will be conversion and ratio. So you'll be able to find both of them on the classroom, all right? Okay, so we're going to first of all write down what we know and what we don't know, fill in the missing values and any totals needed. And then once we've done this, we can then find the scale factor and apply it. So Doesn't make too much sense there because there's not really an example to look at. But let's have a little bit of a look at what this looks like in real life. So it might be a question similar to something like this. So we want to split £180 at a ratio of 5:1. Now, I'm going to show you two different ways of doing this. One way of doing this, and this is my kind of preferred method because it will work even if you have these kind of more backwards ratio problems, is first of all, I'm just going to write down what I know and what I don't know. So I know that I've got 5 pieces and 1 piece here. I don't know what the total is yet. I can work it out very simply, but at the moment, I don't know. And then when I look at the next part, I don't know what that money is going to be split by in the long run, but I do know there's £180 there. So it looks like there's a lot of question marks and a lot of information I don't know, but there's one piece I can find very easy, which is the total. So I can fill in the extra information. I know that in total, this ratio is out of 6. Yeah, if I've got 5 pieces here and 1 piece here, and they're all equal size, so I've got 5 equal pieces, 1 equal piece, in total, I've got 6 pieces. I can then use that to work out the scale. You know, well, if 5 and 1 will give me 6, how many 6s are there essentially in 180? How much bigger has the scale increased by? So to work this out, I'm going to do 180 divided by 6, which will give me 30. So that tells me that all I have to do to work out this is increase my scale by 30 times. The total amount of money has been increased by 30. Therefore, everything that person A is getting has been increased by 30. Everything that person B is getting has also been increased by 30. The answer then will be 15 to 30. And you can check this really easily. You can use a reverse calculation if you want to. So you could do 30 times 6 is 180, etc. Or just look at the parts that you've got. Well, 150 and 30 is 180. So this works very, very well. This is my preferred method of viewing it. Another method of looking at this is to think, first of all, well, I've got 180. That's the amount that I've got here. And then I'm just going to count how many pieces of this ratio I've got. So I've got 5 pieces and 1 piece. So in total, I've got 6 pieces. So I'm going to split that 180 into 6 equal size pieces. So I've got 180. If I divide that by 6, 180 divided by 6, I end up with 30. So it's the exact same sum. It's just a different way of looking at it. So what I've done here then is I've taken my my 180, the total that I've got, I've divided it by 6, and that tells me what one part is worth. I now know that 1 piece is worth 30. I know this person here is getting 1, so he can have 1 of them, that's 30. The other person is going to get the remaining 5. So 5 times 30 will be 150. So 2 different explanations, both explaining the same thing. I prefer the first method because it does help when we actually look at these questions in regards to sometimes you might be given like how much one person is getting, but not what the other's getting or not what the total is. So it can be easier to view it this way, but it is entirely up to you how you view it. Just going to pop up one more quick example then, and then we will have a bit of a look at these. So in this case here then, we've got share £10 between 2 people at a ratio of 2 to 3. This one's a very nice straightforward one. Again, using our kind of second method or our second way of looking at this, we can say, well, in total, if I'm splitting it at 2 to 3, there are 5 pieces. There are 5 pieces in total. So if I take my total, £10, divide it by 5, that tells me that each part is worth 1, or each one part is worth £2. So essentially, I've got this £10, I've split it into different piles, each one having £2. One person's going to get 2 of them, so they're going to get £4. The other person's going to get 3, so they are going to get £6. I can then check this. 4 and 6 is 10. So I know that my ratio is correct. One more problem here. So we've got Julie and Louise, and they make a profit of £90 at a shared stall at a car boot sale, and they agree to share this in the ratio of 4 to 5. How much will they both get? You might be able to spot this one straight away. You know, 4 and 5 will be 9. So therefore, there are 9 pieces. 90 divided by 9 is going to be 10. Each piece is worth £10. Julie's going to get 40. Louise is going to get 50. So quite a nice straightforward one. But again, if you were to kind of write this out in the kind of like the preferred method that I tend to use, it would be, okay, I've got Julie and Louise first of all. I know that the ratio is 4 to 5, and I don't know what the total is. I don't know how much they're both getting, but I know in total there is going to be £90. What I'm then going to do is have a look here and say, well, in total then, there are, Julie and Louise have, in the very simple idea, they have 9. What is the scale factor? Well, 90 divided by 9 tells me that everything is just 10 times bigger. If all of this right-hand side has increased by 10 times, it is equal to all of this on the left. So that is why both of these values will have to increase by 10 times as well. Oh, sorry, that should be a 40. So again, with these as well, and Nicola, that is a really, really good point. So it tends to be these kind of the more worded questions that catch people out. The theory itself is quite nice and straightforward, but this is why all of the assessments that are on the Google Classroom are all from past papers. So the more of the assessments you do, the more used to the style of questioning you'll find it. And also just remember what I said before in regards to even if it's a 3-mark question, you can do the same. Read the question, don't do the maths. Once you've read over the question, then just think, okay, what is it asking me to do? And just bullet point the actual maths that you need to do. I need to find the area, then I need to find 15% of it, and then I need to take that away. Once you do that, you will just focus on each part of the maths in particular, and it will help you focus on. Normally, if we have like a 6-mark question, you try and almost answer the whole thing at once. You're looking at one problem, but your mind's kind of thinking or trying to remember about the next steps you need to do as well. By bullet pointing it, it's almost like making a list. I can't remember everything I need to do. If I write on a list, I don't have to worry because I've got a memory aid. We can do the same with these bigger mark questions. Okay, so hopefully that makes sense then. And one of those explanations will stick with you. Have a go at these questions. Question 1, question 2 are exact ideas of what we've been looking at. Please do use a calculator for these. Again, we've looked at how to multiply and divide. Although this could pop up on the non-calculator, at the minute, it's all about knowing how to answer these. So question 1, question 2, very straightforward. Question 3, we've got 3 parts in this ratio now. Doesn't change anything though, same concept. And question 4 is the idea of this, or introducing this idea of kind of like a backwards kind of relationship here. So have a go, pop over your answers when you can for me, and let's see how we do here. Nicola, yeah, absolutely brilliant. Great start there. So no problems for question 1. And again, with these, even though you might see, slightly stranger looking ratios, it might be a ratio of 3.5 to 2 or something like this. It doesn't matter. The concept is still the exact same. Catherine, yeah, absolutely brilliant there. So again, if you're grasping this idea as well, Catherine, the great thing is this is really the last main topic that we need to review. We're going to look at inverse proportion a little bit, but it's very, very uncommon. So if you do have to duck out a little bit early, no worries. Peace, yeah, they are all absolutely fine. And Catherine, yours for number 2 is absolutely brilliant as well. So great stuff there. Okie dokie. So let's have a little bit of a look at some of these ends. So for our first question then, we should end up with a ratio of 40 to 20 here. Again, it depends how you want to look at this. If you've got £60 in total, you're splitting it into 3 equal pieces because there are 2 pieces and 1 piece. So essentially, we're splitting it into 3 equal pieces, but we're giving them out differently. So that's the whole idea. It is unfair division. We're dividing it fairly, but one person's getting more than the other. Essentially, if you imagine if you'd gone along and you were working somewhere and you got paid £60, if you've done double as much work and your mate's been sat there on the phone most of the time, kind of fair enough that you get paid a bit more. But, you know, that's just my opinion. So, first one will be a ratio of 40 to 20. Nicola, yeah, absolutely brilliant there. So for our next question, you should end up with 360 to 450. It's just to show you that it doesn't matter what the ratio looks like or how much it is, you will still be able to solve these. It might not always be with nice whole numbers. It might have decimals involved. It doesn't matter. You'll still get the same answers. There is a little bit of a shortcut with this one. What you could have noticed is, well, 8 to 10, I can actually simplify that to 4 to 5. So if this is actually a ratio of 4 to 5, it just makes my sums a little bit easier. I can then do, well, 810 divided by 9. And then from that 9, I can then multiply by 4 and multiply by 5. I'll get the same answer because I'm splitting it into less pieces. So each of them is doubly as big. but I'm giving out half as many. So the total amount is still the exact same. Catherine, no problem. And try and get those assessments done. And I'll see you on Monday. No, brilliant. For question 3, then, what we have here is so £24 split at a ratio of 2 to 3 to 1. It's the exact same concept. It doesn't matter that this is being split between 3 different things. It is still the exact same. So I've got 24 divided by 3 will give me £4. Once I've got that 4, I know that is one part. So that's going to be my part on the right. The person on the far left is getting double that. So that's going to be 8. And the person in the middle is getting 3 times that. So that will be 12. So our last question here then, and this is where I tend to prefer to use my method. It just makes a little bit more sense to me. So some money is shared between Tim and his friend at a ratio of 2 to 1. Tim gets £40. So how much was there in total? So it can seem a little bit confusing, although this is a very simplified version of this type of problem. But if I write out what I know and what I don't know, it can make it considerably easier. Sorry, that's got to be capitalized. I can't do that. So Tim and his friend, it's at a ratio of 2 to 1. I don't know how much they've got in total at the minute. I know that Tim got 40 quid. I have no idea what his friend got, and I have no idea how much it was in total. So in regards to this problem, I can say that, well, in total, there was 3 pieces, but it does actually help me because I can't see what the total is, so I can't use that to find my scale. His friend isn't any good either, really, at this point. But what I can do is I can look and go, well, originally, Tim had 2 pieces, or he had 2, and now he's getting 40. So what is the increase? What is the scale that has increased by? If I do 40 divided by 2, I'll find that the scale factor is actually 20. That tells me that everything from the top is increased by 20 to get to here. It's the exact same thing as we've done before. The thing that throws people a little bit is you can work out any of these just from knowing what one part of the ratio is. Because I know that Tim was getting 2 parts and it's 40, I can then work out how much that's increased by, and the increase will be the same for everyone else. Even if they're not earning as much or they're earning more than him, the increase applies to everyone. Everything on this side is equal to everything on this side. So if this is 20 times bigger, then this will also be 20 times bigger. So in total, they will have £60. I can check that and see if it's correct. Well, it's 40 and 20, which is 60. That's where I think this one's probably the best way forward. Another way of viewing this, if you wanted to, is just to think, well, Tim gets £40, and that is equal. Oh, sorry, that looks horrible with all those capitals and stuff there. So Tim gets £40, and that's equal to 2 parts. Therefore, if I divide that, I can find out that 20 is 1 part, and I can then use that to find anything I need. It's just different ways of looking at it. I prefer this kind of method here. I think it's quite nice and straightforward. You can always see exactly what you're doing, but it is personal preference. But for our question there, we should end up with a total of £60. Now, we've just got our last little topic here to look at, which is about inverse proportion. But everything we've looked at so far is the idea of being in proportion. You know, as one thing increases, everything else does as well. Inverse proportion is the opposite. As one thing increases by, let's say, if this goes up by 10 times, this will be decreased by 10 times. If something is doubled on this side, it is halved on this side. It seems like a weird idea, but it applies for certain things. And it is just more a case of reading the question carefully and just thinking about it logically. Like, if I were to increase this, this would also increase. You know, if we were in a shop, if I buy more of something, it costs more money. In some contexts, though, like in this example, that's not true. So let's say I want to build a wall in my garden, and the builders say it's going to take 216 hours to build the wall. So a person hour is the hour worked by one person. Okay, so it's going to take someone 216 hours to build this wall. If I therefore just have one builder it will take them 216 hours to finish the job. Okay, let's think, well, I really need this wool because if not, wildlife's getting into my house and eating stuff from my fridge or whatever they're doing. So what I'm looking at here then is, well, if one builder takes 216 hours, how long will two builders take? If I double the amount of builders, it will half the amount of time. So in this case, two builders will get this job done in, what's that, 108 hours. Brilliant. It might be a case of, I might have to have this job finished in, let's say, it's got to be finished in under 25 hours. So then we can look into that and we go, well, what can we do here then? So, all right, well, how many builders? Let's say I get 10 times as many builders. If one builder can do it in 21 hours, 216 hours, if I have 10 times as many builders, they will build it 10 times as quickly. So it would only take 21.6 hours. If I had 100 builders, it would only take 2 hours or 2.16 hours. So that is the idea of inverse proportion. It is not very common. It is only for level 1 and only for level 2, sorry. And if it does pop up, it's just a case of just reading the question carefully and just thinking, well, what's happening here? And like increase 1, is the other one increasing as well? Most of the time it will, but sometimes you might get a question like this. So let's just have a little bit of a look at it in context then. So I've got this idea of cakes. So we're in a bakery. Each baker can make 50 cakes in 1 hour. How long will it take for the following? So again, the best thing you can always do is write down what you know. So I've got the number of bakers compared to the amount of cakes. And then finally, I've got time. So one baker makes 50 cakes. And I believe it took him, let's have a look, because I've got a screen thing in the way, and it takes him 1 hour to do that. Okay, so we can just use this, but the interesting thing here is certain things will be affected, certain things won't, and it's up to you to choose what is affected. That's where we get our kind of input. Well, how long will it take for 2 bakers to make 50 cakes? Okay, well, if I've doubled the amount of bakers and I've left the amount of cakes the same, that means that they will do that in half the amount of time. Yeah, quite nice and straightforward there. If there's 2 people or double as many people doing the job and they're doing the same job, it will get done twice as quick. There are obviously some generalized assumptions here. So what we assume is that everyone is working at the same rate, everyone is working flat out for the same amount of time, they're not taking breaks or checking their phone, etc. But this is the best we can do with assumptions in maths. It's going to be a bit different in the real world, but as an estimate, this is absolutely fine. So our next question then is a little bit different because we have to kind of look at it in a slightly different way, but there are different ways of viewing it as well. So I've got 3 bakers. How long will it take 3 bakers to make 300 cakes? So what I can do first of all is think, okay, well, if I have 3 bakers and they're all cooking for an hour, they would make 150 cakes in that hour. So therefore, if I've still got the same 3 bakers, but I need them to make 300, they're going to have to work for double as long. Quite nice and straightforward. This is one way of viewing it. What you could view it as well is, well, if I've got 3 bakers, so if I had 1 baker, sorry, let's say I'm going to stick with my 1 baker at the beginning. If he was going to make 300 cakes, it would take him 6 hours. If I then have 3 times as many people doing this, it will reduce the time taken by 3 times. So either way you look at it, you end up with the same answer. For 3 bakers to make 300 cakes, it will take 2 hours. It is just looking at it, what thing do you want to increase? What do you want to decrease? You have the choice there. Okie dokie. So there are a few practice questions at the end here. What I'm going to do in regards to time is I'm going to kind of move over these quickly and just kind of summarize everything. If you are watching this recording, then obviously feel free to load up the PowerPoint, have a look through. There are some really, really good questions in here. But essentially, what we've covered in our session today is we've looked at our ratio. We know what it is now. Okay, it's unfair division. We then looked at how to find equivalent ratios and simplify them. Simplifying is the exact same as with our fractions, and when we find an equivalent, this is really all we're doing when we're dealing with our bigger problems, as we've seen later. We're just saying, well, this is the equivalent ratio to this. What has changed? How much has it increased by? It's almost giving you two different fractions and saying, you know, what's the scale factor? How have I gone from a half to 2/4? Well, I've doubled it. It's just asking you what sum you've done, essentially. We've looked at this in some context then, so we've looked at some basic problems, and we've looked at it in terms of scales and maps. Everyone seemed absolutely fine with that, which is brilliant. And then we've had a bit of a sidestep and we've looked at blueprints. They do tend to use scales. They do tend to obviously be linked in with this. But again, it was worth having a look at there so that you know how to answer this style of question, because they can pop up quite frequently. We've then had a look at pretty much our main point here, which is our ratio division problems. It's all built from our equivalent ratios and everything we've looked at prior. But it's the idea of, you know, you've got your two ways of viewing it now. Either add all the pieces together and find out how many there are. If you then divide by that, then you know what each piece is worth, distribute them how you need to. Or you can look at it in my preferred way, where write out what you know and what you don't know, and it's very easy to spot the links there. Finally, then, we had a little bit of a look at proportion and inverse proportion. I mean, everything that we've looked at so far is in proportion. We just had a look at inverse proportion and how this could look. It's not very common. It's only for level 2 learners. So again, if you are viewing this recording in the future, hello, future people, I would recommend now going and having a look at either some of the practice resources or having a go at the assessment at your level. But that is everything you need to know on ratio. So I'm going to stop recording there.